Hello people, I'm sure you guys must have enjoyed all the different types of new topics that we have accomplished in the chapter Relations and Functions. To test our knowledge about all those concepts clearance, we have 10 questions lined up before us in this session, which actually are JEE main pattern questions. Let's try and explore them and see whether we are able to apply our conceptual knowledge to them and decode them or not. The first question in the league is trying to talk about a certain function f from the collection of all reals, which is acting here as the domain of the function f, and the codomain is given to be minus 1 by 2, 1 by 2 closed interval. Defined as, the rule which this function follows is that whenever it takes an input x from the collection of all reals, because this is what is the valid input set for the function f, it actually returns the output as x upon 1 plus x square. Then this function from this domain to this codomain is invertible, or is it injective but not surjective? Surjective but not injective? Neither injective nor surjective is what the question is trying to say. By invertible, what do I mean? By invertible, I mean that the function should be bijective, both injective and surjective. So in place of invertible, the question would have asked you bijective, or it would have written injective and surjective. All three cases would mean the same thing. Let's see what the function is trying to convey. F is given to be a function from the collection of all reals to minus 1 by 2, 1 by 2 closed interval, such that when f acts upon the real number x, it returns the output x upon 1 plus x square. Now one thing you observe carefully. If you wish to conclude that the function is 1, 1 or on 2, for that particular thing we had done the horizontal line test firstly for 1, 1-ness. But for that it was essential that we have the graph of the function f. Right now there is no scenario like that. Moreover, using the element definition, or I should say fx1 equals fx2 you consider and bring out x1 equals x2, that too is not always possible. Yes, of course it is possible, but not always so feasible option to opt for. And so comes the third option, which you can always try when you have real line given to you as the domain set of the function f. That you can do, which is try, what you just have to try, f of 1 by x is coming out to be f of x or not. For all x belonging to R, x not 0. Because for x 0, 1 by x is not defined and therefore it won't be a real number and so won't be getting an entry inside the function f. This is one method to conclude that the function is not 1, 1. And so if I try and use this method and get this particular thing as the output, that yes, for every x non-zero, f of 1 by x is coming out to be equal to f of x. This would mean that f of 1 by 2 is equal to f of 2. F of 1 by 3 is equal to f of 3. And so many such type of expressions we are going to get. And this would be enough to conclude that f of f defined from R to minus 1 by 2, 1 by 2 with this rule is not following injectivity, because distinct members, 1 by 2 and 2 are distinct. Distinct members of the domain are going to the same member of the codomain. And this is one method to actually say and declare that the function is not 1, 1. Let's try and use this method because right now I can just intuitively assume that maybe this expression will lead to non-injectivity. Let's see if that is true or not. The proof of the claim that I just made, that f of x is equal to f of 1 by x, let's see if that is holding actually or not. If f of x is given by this rule, what do you think is f of 1 by x? Numerator, replace x by 1 by x. You will have this expression, and in the denominator there is 1 plus x square. So you get 1 plus 1 by x whole square, which is this. And you obtain 1 by x whole upon x square plus 1 by x square, which eventually makes the expression equal to this. And this x gets cancelled. You are left with x upon x square plus 1. That is what is holding over here. But what is this? Isn't this equal to f of x? Yes, it is. This means it is true that f of 1 by x is equal to f of x for every x non-zero real number, or I can say r minus singleton 0. And therefore, it is enough to declare that this implies f is not injective or not 1, 1, because this claim's proof leads to this observation that distinct members of the domain are getting mapped to the same member of the codomain. And so, this particular method has actually worked out. You can use another random methods also. For example, if suppose it was very evident for you to say, you could have just directly said that if I substitute 1 by 2 or if I substitute 2, the result will be same. You could have just done that, because from the domain if you pick up or you are able to find 2 or 3 or more than that members getting mapped to the same member in the codomain, that is enough to declare that the function is not 1, 1. If suppose you would have got the graph of the function f and you would have obtained a horizontal line which is intersecting the graph at more than one point, even that would have declared the function is not 1, 1. Here I have just used one of the methods and that has resulted me to the conclusion that f is not injective. So definitely just by this observation, if I go to the options, of course f cannot be invertible because invertible demands function to be both injective and surjective. Well, it cannot be option number B also because it says it is injective but not surjective. So if it is not injective, option B is also wrong. C says it is surjective but not injective. I don't know about that. Neither injective nor surjective. Well, I know it is not injective, but how can I be sure that it is not surjective? That means now we have to definitely move on to check the surjectivity of this function. Let's get ahead with that. If you remember, in order to check about the onto-ness or the surjectivity of the function, it is very much important to actually find the range of the function. And if the range comes out to be equal to the codomain, the function becomes onto. And if the range doesn't come out to be equal to the codomain, the function does not turn out to be onto. Because range being equal to the codomain means that every member of the codomain has at least one pre-image in the domain. So let's get started to finding the range of this function and see whether it coincides with the codomain of f or not. What was the algorithm to find the range of the function? So put y equals f of x. y equals f of x implies y is equal to x upon 1 plus x square. Now, this is y is being expressed in terms of x. Reduce this expression by solving in such a way that x is expressed in terms of y. So, let's do that. You have y multiplied by 1 plus x square equal to x, which implies y plus x square y minus x is 0. I can write this expression as yx square plus minus 1 into x plus y equals 0. Why have I written it like this? Well, if you carefully observe, this y if I call it small a, minus 1 if I call it small b, and y if I call it small c, this expression is basically a particular case of ax square plus bx plus c equals 0. And roots of this quadratic equation, basically the values of x, definitely are coming from the domain of f, which is the collection of all reals. Which means that this equation, where x is coming from the real numbers, that means this has real roots, which implies the discriminant of this, which is b square minus 4ac. This discriminant is greater than equal to 0 as x is belonging to R. By just using this rule, or basically I should say concept, that is what I am going to apply over here. I know this x is coming from the collection of all reals, and this is nothing but an expression of the form ax square plus bx plus c equals 0. That means the discriminant of this equation, which is b square minus 1 square, which is 1, minus 4 into a, which is y, c, which is y, making it 4y square, is greater than equal to 0. Which implies 1 minus 4y square greater than equal to 0 can take place only when 1 is greater than equal to 4y square, or I can say y square is less than equal to 1 by 4. That means y, which is actually standing here as the variable to represent output of the function, its square is always less than equal to 4. That means the function is producing outputs whose square is less than equal to 4. Can I say something about the outputs if I know something about their square? Yes, of course, because I know the graph of y square. That is this. This is the graph of fx equals x square. X and y are just variables. I am just using the concept of graphs to explain you that at minus 1 by 2 and at 1 by 2, at both the points the function obtains the same value, which is 1 by 4. Minus 1 by 2 square is also 1 by 4. 1 by 2 square is also 1 by 4. And that means if I want the values of y to be between 0 and 1 by 4, this can only happen when the values of x are between minus 1 by 2 and 1 by 2. Because only when x varies from minus 1 by 2, 1 by 2, x square varies from 0 to 1 by 4. And that is why if I just consider this as a piece of information coming from the concept of graph of fx equals x square, I know for y square to be less than equal to 4, this is only possible when y is between minus 1 by 2 and 1 by 2. Which means y belongs to minus 1 by 2, 1 by 2. But y was actually the range, and that means when you have put f of x equals to this expression, the outputs which the function is obtaining is nothing but this closed interval minus 1 by 2, 1 by 2, and this implies that the range of the function is minus 1 by 2, 1 by 2, which is equal to the codomain of the function. And that is enough to declare that because the range is equal to the codomain, which is minus 1 by 2, 1 by 2, the function is surjective, and therefore option number D is wrong because it is saying the function is not surjective, whereas the function is definitely surjective. Therefore option number C is correct, which says function is onto but not 1, 1. Making C to be the correct answer. That is what is the concept related to finding the invertibility or finding the 1-1ness and onto-ness of a function defined in this manner. Spend some time with it, understand how I have used the concept of quadratic equations in solving the range part of this function, and then we will proceed for the next question. Beginning with the second question, I have already presented that before you. Why don't you take a look at it and then try and solve it yourself, and then we are going to start the venture of doing it together. What is the question trying to say in this second part? It is trying to give you the value of fkx is this particular expression for k greater than equal to 1. Then for k equal to 4 and for k equal to 6, we have to find f4x and f6x and subtract them and obtain the value and see which of the values are the correct ones. Let's start with this. Fkx is given to be 1 by k sine to the power kx plus cos to the power kx. If this is true for every k greater than equal to 1, definitely f4x we can compute. Just in place of k, substitute 4. You get 1 by 4 sine to the power 4x plus cos to the power 4x. I can write it as 1 by 4 sine square x whole square plus cos square x whole square. And now as you can see, it is very, very easy to say this is acting as A and this is acting as B, and the expression that we have over here is actually A square plus B square. And we know that A square plus B square is nothing but A plus B whole square minus 2AB. Because A plus B whole square is A square plus B square plus twice of AB, therefore A square plus B square comes out to be this, happening to be one of your identities you must be very well aware about. This is what I am going to use over here. My A is nothing but sine square x, B is nothing but cos square x, and therefore A square plus B square happens to be what? A plus B whole square minus twice of A into B, which is sine square x cos square x. All of you know that sine square x plus cos square x is equal to 1. And 1 square is 1 only. So you get this to be equal to 1 minus twice of sine square x cos square x. This is what is your expression turning out to be of f4x, which is nothing but 1 by 4 minus 1 by 2 sine square x cos square x. This is your f4x. It's now time to get along computing what is actually f6x. So let's start computing f6x. f6x, if I start, this is 1 by 6. Just substitute in place of k equals 6. You get sine 6x plus cos 6x, which is equal to what? I can write sine square x whole cube plus cos square x whole cube, because this will be nothing but sine to the power 6x cos to the power 6x. And this now demands for our attention, because this is again acting as A, again acting as B, but now the identity used is A cube plus B cube, which is nothing but A plus B whole cube minus 3AB A plus B. This identity, on using it over here at this step, you get the outcome as 1 by 6, that is already here, A cube plus B cube, which is A plus B sine square x plus cos square x, which is 1. 1 cube, 1 square makes it just 1. Over here cube will come because this is the formula of A plus B whole cube. So when I want A plus B whole cube, it is nothing but sine square x plus cos square x whole cube, which is 1 cube, which is 1, minus thrice of A into B, which is sine square x into cos square x, multiplied by A plus B, which is sine square x plus cos square x, which is again 1. And therefore, what you get is 1 by 6 minus 1 by 2 sine square x cos square x. I am interested in f4x minus f6x. That is what is the demand of the question. Let's compute that. f4x we had already found was 1 by 4 minus 1 by 2 sine square x cos square x minus f6x. f6x is 1 by 6. So you get minus 1 by 6. Further it is trying to say minus 1 by 2 sine square x cos square x. So it becomes plus 1 by 2 sine square x cos square x. And therefore, as you can see, this expression and this expression get cancelled and you are left with 1 by 4 minus 1 by 6, which is nothing but 1 by 12. And that is what is the solution for f4x minus f6x, and that is given as option number D. Therefore, question number 2 is solved in this manner. I have not used anything super great over here. I have just used two very easy identities of a square plus b square and a cube plus b cube and have got the solution straight away. just a question of solving ability, this is how we are going to deal with questions like these. Let's see what we have in the league as the next very question waiting for our attention. The next question says, which of the following relations on R, here R is standing for the real line, is an equivalence relation? In one, A is related to B if and only if distance of A from 0 is equal to distance of B from 0. Let's see if R1 is an equivalence relation or not. It says A is related to B if and only if distance of A from 0 is equal to distance of B from 0 on the real line. Beginning with reflexivity, let's see if A is related to A by this relation. That means I have to show distance of A from 0 is equal to distance of A from 0. And this I have to show for every real number. This is true. Distance of A from 0 is of course equal to distance from 0 of the same number A. And therefore, because this is already true, this implies R1 is reflexive. Talking about symmetricity, I am saying let A be related to B under the relation R1. This means distance of A from 0 is equal to distance of B from 0. Obviously, this relation can also be read as B is related to A, because distance of B from 0 is obviously equal to distance of A from 0 if you read it in any way. And therefore, R1 is symmetric. Transitivity is very obvious. Why? Because if you say that distance of A from 0 is equal to distance of B from 0 and distance of B from 0 is equal to distance of C from 0. Why have I written this? Because if I am assuming A is related to B under the relation R1 and B is related to C under the relation R1, then obviously this implies if mod A is equal to mod B is equal to mod C, this obviously implies mod A is equal to mod C, or I can say A is related to C by the relation R1, and this implies R1 is transitive. Because R1 is reflexive, symmetric and transitive, R1 is an equivalence relation. Let us see if B is an equivalence relation or not. Here it is saying A is related to B if and only if A is greater than equal to B. Well, that is what is my R2. A is related to B if and only if A is greater than equal to B. Either greater than or equal to. Well, obviously this relation is reflexive because A is greater than or equal to A. So, because A is equal to A, therefore A is greater than equal to A. So, A is related to A. So, this relation is definitely reflexive. What about symmetric? Well, I know 2 is greater than 3. Therefore, 2 is greater than or equal to 3. But This means 2 is related to 3 under the relation R2. But because 3 is not greater than or equal to 2. Can I say that? Well, of course not. Here I have written 2 is greater than or equal to 3, which is wrong. Actually, it is 3 is greater than or equal to 2. If 3 is greater than or equal to 2, I can say that 3 is related to 2 under the relation R2. But 3 is related to 2 under the relation R2. Does this imply 2 is related to 3 under the relation R2? For that, I need is 2 greater than or equal to 3 or not? Well, not at all. 2 is neither greater than nor equal to 3. Therefore, 2 is not greater than or equal to 3, which implies 2 is not related to 3 under the relation R2. And this means 3, 2 belongs to R2, but 2, 3 does not belong to R2, and therefore R2 is not symmetric. And the moment you have with you that R2 is not symmetric, it definitely cannot be equivalence relation, because for equivalence, I need reflexivity, symmetricity and transitivity. R2 is not symmetric, so R2 cannot be equivalence relation. If you try and observe R3, I have A divides B, only then A is related to B. Can you conclude that this is reflexive? Yes, of course, because A always divides itself, right? But if 2 divides 4, does 4 divide 2? Of course, 2 divides 4. You can divide 4 by 2 and get the remainder 0. So, 2 completely divides 4. But does this imply 4 divides 2? Not at all. And that is why R3 is also implying that 2, 4 belongs to R3, but 4, 2 does not belong to R3. So, just like the previous case, R3 is also not symmetric and therefore not equivalence relation. If I talk about D, here it is saying A is less than B, only then A is related to B. 2 is less than 3. Does this imply 3 is less than 2? Not at all, and therefore this implies 2, 3 is in R4, but 3, 2 is not in R4, which means this relation is again not symmetric and therefore not equivalence relation. And so it was very natural to actually see that among all these 4 relations given to us, only one relation came out to be actually equivalence relation, which said that A is related to B only when the distances of both A and B from 0 are the same. The rest of them, talking about inequalities, failed actually to become equivalence relations. Why? Because they were not turning out to be even symmetric, forget about equivalence. Let's deal with the next question, which is talking about number of onto functions. I have already taught you how to find number of one functions, number of onto functions, number of many one functions and number of into functions. Among all these 4 formulas which we had developed, right now the question is demanding the formula for number of onto functions from E to F. I told you the concept is, let cardinality of A be M and cardinality of B be N, then total number of functions from A to B is equal to cardinality of B raised to the power cardinality of A, which is n to the power m. And total number of onto functions was nothing but total number of functions, which is n to the power m, minus total number of into functions. What is the formula for total number of into functions? Well, it is summation NCR minus 1 to the power r minus 1 n minus r to the power m, where r varies from 1 to n. This is total number of functions. This is total number of into functions. From the total number of functions, when you subtract number of into functions, you get number of onto functions. Right now, I have to find number of onto functions from E to F. So, let's apply this particular formula. Here, role of A is being played by the set E, and set E has how many members? 4 members. So, cardinality of E is 4, which is playing the role of M, and cardinality of F is 2, which is playing the role of N. And so, total number of onto functions from E to F is n to the power m, which is 2 to the power 4 minus summation NCR, so 2CR minus 1 to the power r minus 1 n minus r, that means 2 minus r to the power m, m over here is 4, where r varies from 1 to n, n is 2. This is what is the formula in this case. And so, what is it that you get is 2 to the power 4 makes it 16 minus, for r equal to 1, what is it that you get? You get 2c1 minus 1 to the power 1 minus 1, which is 0. So, minus 1 to the power 0 makes it 1 into 2 minus 1, which is 1. 1 to the power 4 is again 1. So, over here you just get 2c1 plus, now substitute in place of r, 2 you substitute. You get 2c2 minus 1 to the power 2 minus 1, that means minus 1 to the power 1, 2 minus 2, which makes it 0. So, this is it. That's it. Only up till 2 we were allowed to go, so we went only up till 2. So, this happens to be 16. What is 2c1? Well, 2c1 is 2 factorial upon 1 factorial into 2 minus 1 factorial, which is again 1 factorial, and that is nothing but 2. And so, you get 2c1 is equal to 2, thereby giving you 2 over here, plus 0 into anything is 0. And you get 16 minus 2, that is 14. Out of total number of functions, only 2 were into functions, rest of them, which is 14, are onto functions, and that is why total number of onto functions from E to F with E's cardinality as 4, F's cardinality as 2, it is 14. That is how you deal with this easy question just by applying your formula to find total number of onto functions from A to B. This concept is very important. Many a times questions are asked based on this concept, and this was just about understanding how to deal with such questions. Next question will be posed before you, but only when you sit with this, understand this, practice it and write it in your notebooks very nicely. Let us see what the next question has to bring for us. The next question, just give it a reading and then try and understand what is the question's demand. Question number 5 is actually giving you already GOF of x as mod of sin x and FOG of x as sin square root x. And then it is saying if GOF for some g and some f is coming out to be this and FOG for the same f and the same g is coming out to be this, then is f this and g this, or f is this and g is this? What is f and what is g is what is the question trying to say, or there are no f and no g which on getting composed get these as the results. That is what we have to see. Let's start with the first A option, which gives f is sin square x and g is root x. A says f is sin square x and g is root x. In that case, let's see with this f and this g, what is FOG and what is GOF. So FOG of x is f of g of x, which is f of root x, and f, what does f do with any input? Sine square of that input. So this is sine square root x, which can be written as sine of root x whole square. And this is the given FOG to you, sine square root x. That means with this f and this g, definitely FOG is coming out to be sine square root x. Let's see if GOF is coming out to be mod of sine x or not. GOF of x is nothing but g of f of x, which is, what is f of x? It is sine square x. And what is g doing? It is taking under root of the input, so under root of sine square x. And now is the turn to use a very small concept which says under root of x square is always equal to mod x. And based on that, I can write this as mod of sin x. And this means with this f and this g, FOG is coming out to be what I wanted, and with the same f and same g, GOF is coming out to be what I wanted. That means there is an f and g corresponding to which FOG is sine square root x and GOF is mod sin x, and so this option is definitely wrong, which is f and g cannot be determined, and A is correct. What about B and C? Let's see if any one among them is correct or not. F is given to be sin x, G is given to be mod x. What is FOG? Let's see. F of g of x, which is f of mod x, which means sine of mod x. I want FOG to be equal to sine square root x. Definitely with fx equals sine x and gx equals mod x, FOG is not coming out to be this. Let's see what is GOF. G of f of x, which is mod of sine x. So yes, This f and this g are definitely giving the GOF that I want, but they are not giving the FOG that I want, and therefore this cannot be the correct answer. If I talk about C, C says f is x square and g is sine of root x. Let's see if they give you the correct answer or not. Fx is given to be x square and gx is sine of root x. In this case, FOG of x is f of sine of root x, which is sine of root x whole square, which is definitely the FOG that I want. And if I talk about GOF of x, this is nothing but g of x square, which is what? Sine of under root x square, right? G of f of x, which is sine of under root x square, and I just now told you this is nothing but sine of mod x, right? That means this is definitely not equal to mod of sine x, because mod of sine x is only allowed to take non-negative values, but sine of mod x can take negative values also, and so this is not the GOF that I want. So with this f and this g, FOG is coming out to be what I want, but GOF is not what I want, and that means option number B and option number C do not provide me with f and g, which make both these compositions true, and so only A has f and g, which makes both these compositions true, and that is why A is the correct answer. This is how nicely we dealt with this question and then successfully obtained the answer related to the composition part of the chapter, Relations and Functions. Let's see what the next question is trying to demand from us. The next question speaks about a relation. It is saying if S is defined on the collection of all reals by this particular rule, that x comma y belongs to S provided x into y is non-negative, then S is what? First thing that I wish to tell you is, whenever I say x and y are two real numbers whose product is non-negative, this means x is positive and y is positive, or x is negative and y is also negative. What do I mean by this? Product of two real numbers can be non-negative only if both of them have the same sign. If x is positive, y is negative, or x is negative, y is positive, the product will be negative and not non-negative. That means for the product of two real numbers to be non-negative, both of them should have the same sign. Only then can the product be non-negative. That is what is the case. Now let's understand whether the relation given is equivalence relation or not. It is given x is related to y under the relation S provided their product is non-negative. Firstly, I have to show x is related to x for every real number x. That means I have to show that x into x, which is x square, is non-negative. This is true for all x in R. I know that x square is definitely non-negative. We also know the graph of x square. it only obtains non-negative values in its output, and that is why this is true, which implies relation S is reflexive. If I talk about symmetricity, I will say let x be related to y under the relation S, which means let x into y be non-negative. This means x and y have the same sign. Now if x into y is non-negative, I know in real numbers x into y is same as y into x, and so I can write it as y into x is non-negative, which would imply y is related to x under the relation S, and that is what I wanted to show. If x comma y belongs to S, this implies y comma x also belongs to S, and this means S is symmetric. The last thing left is transitivity. What do we mean by transitive? So let A be related to B under the relation S and B is related to C under the relation S. I have to show A is related to C under the relation S. If A is related to B by S, this implies A into B is non-negative, and B is related to C, that means B into C is non-negative, right? Now if A into B is non-negative, this means A and B have the same sign. Either A and B both are positive or A and B both are negative. Similarly, if B into C is non-negative, this implies B and C have the same sign. That means if B is positive, C is also positive. If B is negative, C is also negative. For B into C to be non-negative. Let's take any case. Suppose A is positive and B is also positive. That means both have the same sign of plus. So if A is positive, B is also positive because A into B has to be non-negative. If both A and B are positive, if I come to the next expression, already if I have B positive declared, that means B will be positive here. And if B is positive here, C has to be positive to give out B into C non-negative. That means I had taken A as positive, because of which B turned out to be positive, for A into B to be non-negative. This means A and B both are positive, which means B and C both are positive, to give B into C as non-negative, which means A and C both are positive, which means A and C have the same sign. Similarly, you can do it with minus sign, and you can get, if A has a minus sign, to give non-negative output, B also should have a minus sign, and if B has a minus sign, to give a non-negative output, C should also have minus sign, which means A and C both have minus sign. Because A and C have the same sign, A into C is non-negative in that case also. So in both the cases, I am sure A and C will have same sign, because of which A into C will be non-negative, or I can say A is related to C under the relation S, which implies S is transitive. And therefore, my S, which is given to me, is reflexive, symmetric and transitive. Therefore, this S given to me is definitely an equivalence relation. I will be taking you to the next question, but only when you spend some time with it, understand what I have done and write it down in your notebooks. Starting with the next question, just take a look at what it is and then I am going to tell you how to deal with it. Question number 7 is trying to give you an expression of the function in some unknown. It is saying that f of x is equal to alpha x upon x plus 1, where obviously x is not allowed to be minus 1, because if you put x equals minus 1, you get denominator as 0, and therefore this expression doesn't land inside real numbers. Then for what value of alpha f of x is equal to x? I want that alpha which can make the composition of f with itself equal to the identity function. Because identity of x is equal to x, I want FOF, that is what I want. In the solution, the target is FOF is equal to identity. This is what I have to show. Let's see what is f of f actually. So, FOF of x, which is f of x, where f of x is alpha x upon x plus 1. Let's now apply f to this expression. You get alpha into alpha x upon x plus 1 whole upon alpha x upon x plus 1 plus 1. That's it. Now just open it up, solve it further. You get alpha square x upon x plus 1 whole upon alpha x plus 1 whole upon x plus 1. Cancel this out. What is it that you get? You get alpha square x upon alpha x plus 1. So you can take out x common, alpha plus 1 plus 1. If you want FOF of x to be equal to x, this is what is my FOF of x. That is what we have attained by solving it. If I want this to be equal to x, this means what? This means just cross multiply, you get alpha square x on the left hand side equals x square times alpha plus 1 plus x. That's it. That means for FOF of x to be equal to x, this equation should be satisfied. That means alpha square x minus x square times alpha plus 1 minus x should be 0. Now, this means what? Well, if I want FOF of x to be equal to x for every x, this means for every x, this equation should be satisfied. And this means if I just take out x common, you have alpha square minus x times alpha plus 1 minus 1 equals 0, which gives you x. Outside you have, here you can just write this as this plus alpha square minus 1. But you know what is a square minus b square, because I can write 1 as 1 square. So this happens to be x common minus x times alpha plus 1 plus a plus b into a minus b is a square minus b square. This is what you get, which further implies you get alpha plus 1 is common. Just look at here in both these expressions, you get alpha plus 1, take it out common, inside you get minus x plus alpha minus 1 equals 0. This means what? Well, this means x is 0 alpha is minus 1 and alpha is 1 plus x. Just equate each term to 0. If x is 0, this means alpha is 1 plus 0, which is 1. So from here you're getting alpha is minus 1 and alpha is 1. But if you substitute alpha as 1, do you get FOF of x equals x? This expression is basically trying to say that for FOF of x to be equal to x, alpha has to be minus 1 or 1. And now, if I wish to say which among these two alphas is the correct alpha, what do I need to do is, I have to verify for which alpha when I substitute in the expression, I am getting FOF of x to be equal to x. Let's do that for alpha equal to 1 firstly. If I try and do it over here, I have f of x equals alpha x upon 1 plus x. That is what I wish to do. So with alpha equals 1, I have x upon 1 plus x as my f of x. So I have f of x equals x upon 1 plus x. And FOF of x turns out to be what? It turns out to be x upon 1 plus x whole upon 1 plus x upon 1 plus x. That is what it turns out to be, which is nothing but x upon 1 plus 2x. And this is not equal to x for every x. Because fx for alpha equals 1 is not giving you that FOF of x is equals x, it is giving you FOF of x is x upon 1 plus 2x, which is not equal to x. That means alpha equals 1 is not the correct value of alpha. Whereas if in this particular f, which is alpha x upon x plus 1, I try and incorporate alpha equals minus 1 as alternative option, then fx equals alpha x upon 1 plus x with alpha equal to minus 1 gives me minus x upon 1 plus x as my f of x. And so f of x becomes minus or f of minus x upon 1 plus x. That means I have in place of x minus x upon 1 plus x whole upon 1 plus minus x upon 1 plus x, which is x upon 1 plus x whole upon 1 plus x minus x, which means 1 upon 1 plus x, giving you x upon 1, which is x. That means for alpha equal to 1, you are getting that FOF of x is equal to x, and so among the two values of alpha, which was alpha equals minus 1 and alpha equals 1, this is wrong because corresponding to alpha equals 1, FOF of x is not coming out to be equal to x, and that is why the correct option is not C but D. For alpha equals minus 1, I have this expression coming out to be equal to x, that is I have f of x to be equal to x. We were obtaining two values of alpha in our solution, but out of them only one is coming out to be true because corresponding to the other one, FOF of x is not coming out to be equal to x, and that is what is our demand. Let's see what is the next question's demand for us. Question number 8 is giving you the function as cos of log x. Then it is saying compute this expression. This expression has which value? Let's just substitute and start computing. we have f of x equals cos of log x. In that case, what is fx into fy? Firstly, if I wish to calculate fx into fy, this is cos of log x into cos of log y. And in the next expression, I wish to calculate half of f of x by y plus f of x into y. Let's see what that is. This is nothing but half of f of x by y, which means cos of log of x by y plus cos of log of x into y. But you know that already cos of m by n is log of m by n is log m minus log n. So log of x by y turns out to be log x minus log y plus log of m into n is what? Log of m into n is log m plus log n. And this is what it becomes. Now what I am going to use is a very nice identity, which is cos c plus cos d. Whenever you have something like cos c plus cos d, that means sum of two cosine functions, how can you change it into product of cosine? Well, this happens to be 2 cos c plus d by 2 multiplied by cos c minus d by 2. Just using this identity, because I have with me cos c, here this is playing the role of c, plus cos d with a 1 by 2 standing outside. You have 1 by 2 cos c plus cos d, which is 2 cos c plus d. Now this is c, so you have log x minus log y. C plus d. D is this, which is log x plus log y. C plus d by 2 multiplied by cos of c minus d. So c is log x minus log y minus d, which is log x plus log y. So you have minus log x minus log y by 2. So what is it that you get? You have log y getting cancelled, and here you have log x getting cancelled. And you are left with this 2 also getting cancelled. You have cos of log x plus log x 2 log x by 2 into cos of minus log y minus 2 log y by 2, which is cos of minus 2 log y by 2. This gets cancelled. You are left with cos of log x into cos of minus theta, which is cos theta, which is cos of log y. And therefore, in 1, which is fx into fy, you had cos log x into cos log y, and with the help of this second expression also, you have cos log x into cos log y. You are supposed to subtract them That means you are subtracting cos log x cos log y minus cos log x cos log y. That means you are obtaining as your solution option number which one? A says that this has value -1. No, it doesn't have -1. 1 by 2? No. -2? No. The answer is because the value is 0 of this expression. 0 is not covered in any of the options. So none of these is the correct answer. That's it. You have to compute in this manner this question. We are going to start the next question, but only when you spend some time with it. Do some calculations involved over here, understand what I have done and be prepared for the next question. After understanding the concept of this particular question, let's see what the next question lined up for us is. Over here we are given the set of all reals denoted by the letter S, and R is a relation which says that A is related to B under the relation R provided the distance between A and B is less than or equal to 1. Then we have to check that this relation follows the rules of reflexivity, symmetricity, transitivity, which among all these three this relation holds the rules of. Let's start with the very first thing, that is checking whether this relation is reflexive or not. For that, we need to show A is related to A for every A belonging to the set of all reals, which here is denoted by S. That means I have to show distance between A and A is less than equal to 1. Obviously, distance between A and A is 0, which is obviously less than equal to 1, which implies R is definitely reflexive. Once I know R is reflexive, option number C definitely is wrong because it says R is symmetric, transitive but not reflexive. But my R is reflexive, so C is wrong. Let's check about symmetricity and transitivity. Let A be related to B. This implies distance between A and B is less than equal to 1. Now you obviously know that distance between A and B is same as distance between B and A, which will obviously be less than equal to 1. But mathematically, if you wish to prove it, you can write this as minus of B minus A. The same A minus B can be written as minus of B minus A. But mod of negative comes out to be what? Well, mod of minus x is same as mod of x. So this is nothing but modulus of B minus A. And therefore, because mod of A minus B was only written like this, which is nothing but mod of B minus A, that is why you have mod of A minus B is coming out to be equal to mod of B minus A, and because mod of A minus B is less than equal to 1, you have mod of B minus A is also less than equal to 1, which implies if A is related to B, B is related to A, which implies R is symmetric. So that means yes, R is definitely reflexive and symmetric. Let's check if it is transitive or not. Let A be related to B and B be related to C. This implies distance between A and B is less than equal to 1 and distance between B and C is less than equal to 1. Does this imply distance between A and C is also less than equal to 1? Let's check it out. Consider distance between A and C. This expression can be written as A minus B plus B minus C, right? Add and subtract B, which is what? If you remember, triangle inequality related to the mod function says that mod of x plus y is less than equal to mod x plus mod y. That is what is known as the triangle inequality. Which if I try and use over here makes this x, y and mod of x plus y is less than equal to mod x plus mod y. But mod of a minus b is less than equal to 1 and mod of b minus b is again less than equal to 1. So, mod of a minus b plus mod of b minus c is less than equal to 1 plus 1, which is 2. It is coming out that distance between A and C is less than or equal to 2. It is not definitely less than or equal to 1. That means A is not related to C under the relation R, or I can say R is not transitive. And thus, what I have as the correct answer is that yes, R is reflexive, yes, it is symmetric, but no, it's not transitive. B says it is reflexive and transitive. No, it's not transitive. C is already wrong and D is also wrong because D requires the relation to be reflexive also, symmetric also and transitive also. And because this relation is not transitive, that is why it cannot be an equivalence relation, and thus option number D holds wrong. The next question, the very last one in the league, talks about what? It is trying to again give you two functions. It is saying suppose fx is sin x plus cos x, gx is x square minus 1, then what do you think about the injectivity and surjectivity of GOF of x? In fact, it doesn't ask you that, it is already giving you that this is invertible in which domain? Let's try and decode this question. You are given fx equals sin x plus cos x. And you are given gx to be x square minus 1. Then the question is talking about the composition GOF of x. In order to answer the question about where is it invertible, first let's see what is GOF of x, which is G of f of x. F of x is sin x plus cos x, and this is nothing but its square minus 1. So it is sin x plus cos x whole square minus 1, which is nothing but sin square x plus cos square x plus 2 sin x cos x minus 1. But sin square x plus cos square x is 1. You already have minus 1 here. So this 1 and this minus 1 gets cancelled. You are left with twice of sin x into cos x, which is nothing but the formula of sin 2x. you have GOF of x coming out to be sine 2x. Where is this function invertible? Invertible in which domain? Which domain is there which is making this function sine 2x 1, 1 and on 2? Well, if I give you a small review about inverse of the sine function, let me tell you that over the entire domain, sine function is not 1, 1. Because if you take the domain to be collection of all reals, then it does not pass the horizontal line test. Any horizontal line that you draw cuts the graph at infinitely many points. And thus we use the method of restriction to make sine invertible. We restrict sine to the interval minus pi by 2, pi by 2. Because when you restrict sine to the interval minus pi by 2, pi by 2, that means you shorten the domain of sine corresponding to this domain, the sine function reacts in this manner. That means it is no more having any turns and it passes the horizontal line test, and that is why this sine function from this domain, which is minus pi by 2, pi by 2, 2 minus 1, 1, happens to be both 1 to 1 and on 2, and hence invertible. So this means x, which is the input for sine, should come from minus pi by 2, pi by 2 for sine x to be invertible. That means I can write for sine x to be invertible, where should x come from? X should come from the domain of sine corresponding to which 1-1ness is being established and on-2ness is being established. So for sine x to be invertible, x should belong to minus pi by 2, pi by 2, or x should be greater than equal to minus pi by 2 and less than equal to pi by 2. So this implies for sine 2x to be invertible, which is the argument of sine function over here, this is acting as the input. So the input should come from minus pi by 2, pi by 2, or it implies x should come from minus pi by 4 to pi by 4. That means corresponding to the input set minus pi by 4 closed interval, I can guarantee that sine 2x is invertible. And so the domain which is making sine 2x invertible is minus pi by 4 closed interval, and sine 2x is what is my GOF. So the interval which is making GOF invertible, or the domain which is making GOF invertible, is minus pi by 4 pi by 4. That is what is the case over here in this particular question. I wanted that domain which is making GOF invertible with the help of using the concept of sine being invertible, where we have established where will GOF be invertible and which makes B to be the correct option. This brings me to an end of the discussion of these questions. I hope you had fun applying all your concepts in all these questions. This basically demands your revision about the concepts if you were not able to do them properly, and practice of these questions thoroughly. See you next time. Till then, keep studying hard. Goodbye.